Once more, we return to the dark, that quiet above you, the one you thought you knew. Look up tonight, into a patch of sky no larger than a grain of sand held at arm's length. Where your eye sees nothing, a telescope finds 10,000 galaxies, each one an island of billions of stars, billions of light years away. The darkness between them is not empty. It is filled with light you cannot see, with matter that emits nothing, with distances so vast that 13 billion years of travel at the speed of light would not be enough to cross them. Tonight, I want to show you that the darkness above you is not empty. It is the shape of everything the universe has become, and the answer to a question that unsettled astronomers for 300 years. If you find yourself returning to these journeys, leave a small like behind, a like, a subscription, so others might find their way here too. Now dim the lights. Settle into the quiet. Let your breathing slow. We are going to trace the riddle of the dark night sky, the question that unsettled astronomers for 300 years, and the answer that revealed a universe with an age, a horizon, and a constitution mostly beyond light. You do not need to follow every word. Close your eyes when you are ready. The darkness is not emptiness, it is a signature, written in the structure of space and time. I am the cartographer of the dark. I have been mapping these distant places for longer than I can remember, tracing the boundaries where light ends and the void begins. You are here now, and we will walk this together. Look up at the night sky on a clear evening far from city lights. The stars scatter across the black like salt on velvet. The darkness between them seems natural, almost expected. But for more than 3 centuries, that darkness was one of the deepest unsolved riddles in all of physics. Because according to the mathematics of an infinite, eternal, static universe filled uniformly with stars, the night sky should not be dark at all. It should be as bright as the surface of the sun. This is the heart of the dark sky riddle. The logic is simple, almost unavoidable. Imagine looking out in any direction from Earth. Your line of sight travels through space. In an infinite universe uniformly populated with stars, that line must eventually, inevitably, terminate at the surface of a star. Not empty space. Not darkness. A star. Now consider every direction at once. Every point in the sky, wall to wall, horizon to horizon, should resolve to starlight. The entire dome of night should blaze with the combined radiance of every star in an infinite cosmos, their surfaces tiled edge to edge across your vision. The sky should be a furnace. The mathematics makes this inescapable. Consider the geometry. The farther out you look, the more stars you find. The number of stars at a given distance grows with the square of that distance. But each star also appears dimmer the farther away it is, fading with the square of distance in exactly the same proportion. The two effects cancel precisely. Every shell of space, near or far, contributes the same amount of light. Shell by shell, the sky should fill with light. Add them together, stretching out to infinity, and the brightness accumulates without limit. Yet when you look up tonight, you see darkness. The math was sound. The assumption was wrong. The problem first surfaced in 1576, raised by the English astronomer Thomas Digges. He pondered an infinite cosmos and wondered why the night remained dark. Johannes Kepler returned to the question in 1610, troubled by the same contradiction. Edmund Halley examined it in 1720, bringing the tools of Newton's new physics to bear. Jean-Philippe Loy-de-Chercy gave it a more formal mathematical treatment in 1744, calculating the expected brightness and finding it incompatible with observation. But it was Heinrich Wilhelm Olbers who gave the riddle its lasting name. In 1823, Olbers published an essay titled concerning the transparency of space. And though he was neither the first to pose the question nor the one who ultimately solved it, the paradox has carried his name ever since. Olbers gave the riddle its name in 1823, but the question had unsettled astronomers for more than 2 centuries before him. What made the riddle so stubborn was not its complexity, but its clarity. It rested on 3 foundational assumptions about the universe: that space extends infinitely in all directions, that time stretches infinitely into the past, and that stars are distributed uniformly throughout that infinite expanse. If all 3 were true, the night sky could not be dark. The darkness you see tonight is direct observational evidence that at least one of those assumptions must be false. The sky itself is testimony. The black between the stars is not a gap in the data, it is the data. Olbers himself proposed a solution. He suggested that interstellar dust absorbs the light from distant stars, preventing it from reaching Earth. It was a reasonable guess. Space is not perfectly transparent. Dust clouds do block starlight, dimming the glow of the Milky Way in certain directions, hiding whole regions of the galactic plane. But the solution came apart at the level of thermodynamics. In an eternal universe, dust does not simply swallow light and hold it. Dust absorbs energy, heats up, and eventually reaches thermal equilibrium with the surrounding radiation field. At that point, it re-emits exactly the same energy it absorbs. The brightness does not disappear, it only changes form. The sky would still blaze, not with visible light perhaps, but with infrared radiation from heated dust glowing at the temperature of starlight. The darkness would not survive. Kepler had tried another approach. He proposed that the universe is finite in spatial extent, that the stars simply run out at some distance. Mathematically, this truncates the infinite sum. The brightness remains finite, the sky stays dark, but a finite, static universe is unstable. Without expansion to balance gravity, it collapses under its own weight. The stars would fall toward one another, drawn inward by their mutual attraction. Kepler's solution worked on paper, but not in space. For centuries, every answer left the universe eternal. And an eternal universe, no matter how it was dressed, filled the sky with light. Then, in 1848, something unexpected happened. Edgar Allan Poe, better known as a poet than a cosmologist, published a prose poem titled Eureka. In it, he argued that the dark voids in the sky could only be explained if light from the most distant stars had not yet had time to reach us. He grasped intuitively what the astronomers of his generation had not formalized: that light travels at a finite speed, and that if the universe had a beginning, there would be a boundary beyond which no light had yet arrived. A poet came closer to the answer than the astronomers of his generation. A decade later, in 1858, the German astronomer Johann Heinrich von Madler published the first solution in scientific literature. He combined the finite speed of light with the hypothesis that stars had not always existed. If we knew the moment of creation, he wrote, we should be able to calculate its boundary. It was qualitative, not yet a complete physical demonstration, but it pointed in the right direction. The darkness was not a failure of the universe to fill with stars. It was a signature of the universe having an age. The riddle resisted resolution for nearly 300 years, not because astronomers were careless, but because every proposed solution implicitly preserved the assumption of an eternal universe. The correct answer required abandoning that assumption entirely. And that became possible only after 1929, when Edwin Hubble demonstrated that the universe is expanding, that galaxies are receding from one another, that the cosmos has a history, and therefore an age. The night sky is dark because the universe has not had infinite time to flood it with light. The stars have been shining for a finite duration, Light has been traveling for a finite duration, and in that span, only so much light has had the opportunity to arrive. The geometry that seemed to demand a blazing sky assumed an eternal past. Remove that assumption, and the infinite sum collapses. The shells of space no longer extend without limit into time. They are bounded by the age of the universe itself, by the moment when the first stars ignited, by the speed at which their light has been able to travel since. The darkness becomes not a paradox but a prediction, not an anomaly but an inevitability. The math that proved the sky should be bright was never wrong. It was conditional. It described what an infinite, eternal, static universe would look like. And the darkness you see tonight is the universe's answer. I am none of those things. The riddle of the dark sky is not merely a historical curiosity, not a puzzle solved and filed away. It is a window. It opened onto questions that reshaped our understanding of time, space, and the constitution of the cosmos. The darkness between the stars is not emptiness. It is a physical signature of a universe, with an age, with an expansion, with a composition mostly beyond the reach of light. The sky is dark because the universe is young enough that light has not had time to arrive from every possible source. The sky is dark because space itself is expanding, stretching the light that does arrive into wavelengths the human eye was never built to see. The sky is dark because most of the universe emits nothing at all. Each of these answers leads deeper. The finite age of the universe implies a beginning, a moment before which there were no stars, no galaxies, no light. The expansion of space implies a history, a trajectory, a cosmos in motion, rather than at rest. The composition of the universe, as we will see, implies that visible matter is a minority constituent, a thin luminous thread woven through a fabric made mostly of things that do not shine. The stars you see tonight are islands. The ocean between them is not nothing. It is the shape of a universe with an age, with boundaries, with a constitution mostly beyond light. The riddle that took 3 centuries to solve was never about why the sky fails to be bright. It was about what the darkness means. And the answer, when it finally came, was not a correction but a revelation. The night is dark because the universe is real, because it has a history, because light moves at a finite speed through a space that itself is moving. The darkness is not a flaw. It is a signature. It is the shape of time made visible. We pause here for a moment. Wherever you are tonight, the stars above you trace constellations that belong only to your latitude, your season, your hemisphere. If you feel moved to, leave your city and your local time below. The cartographer is genuinely curious where this voice finds you. For 300 years, astronomers tried to solve the riddle of the dark sky. Every answer they proposed seemed reasonable. Every answer came apart under scrutiny. And every answer, without exception, left the universe eternal. The first solution came from Jean-Philippe Loy de Chazot in 1744, and again from Heinrich Wilhelm Olbers in 1823. They proposed that interstellar dust absorbed the light from distant stars before it could reach us. The darkness, they argued, was simply the shadow cast by clouds of matter drifting between the stars. Dust fills the space between suns. Light strikes it, the dust swallows it, and the sky remains dark. It was a reasonable guess. It came apart at the level of thermodynamics. John Herschel demonstrated the flaw in 1848. In an eternal universe, dust does not simply swallow light and vanish it into nothing. Dust absorbs energy, heats up, and eventually reaches thermal equilibrium with the surrounding starlight. At that point, it re-emits exactly the energy it absorbs. The brightness does not disappear, it changes form. every grain becomes a tiny ember. The sky would still be full of light, radiating from every mote of dust as if the dust itself were glowing. The solution preserved the riddle it was meant to resolve. Johannes Kepler, more than 2 centuries earlier in 1610, had proposed something simpler and more radical. Perhaps the universe was finite in spatial extent. Perhaps the stars simply ran out at some distance, and beyond that boundary lay nothing but void. Mathematically, this resolves the riddle cleanly. If space ends, the sum of starlight terminates. The sky can be dark. But a static, finite universe collapses under its own gravity. Every star pulls on every other star. Without expansion to counteract the inward pull, the entire cosmos would contract and fall together. Kepler's universe was geometrically correct, but physically unstable. It could not persist. The solution required something that would not be discovered for another 300 years. That the universe was expanding, and that expansion could hold the collapse at bay. And then, in 1848, a poet came closer to the answer than the astronomers of his generation. Edgar Allan Poe published a prose poem titled Eureka. In it, he argued that the dark voids in the sky could only be explained if light from the most distant stars had not yet had time to reach us. He grasped the finite speed of light as the key. He understood, intuitively, that the universe might have an age, and that this age imposed a horizon. Light travels. It does not arrive instantaneously. If the cosmos had a beginning, then there must be stars so distant that their light is still traveling toward us through the void. The darkness, Poe argued, was not absence. It was delay. It was the signature of distance measured in time. He did not have the mathematics. He did not have the observational evidence. But he saw the shape of the answer decades before the astronomers did. 10 years later, in 1858, Johann Heinrich von Mädler published the first solution in scientific literature. He combined the finite speed of light with the hypothesis that stars had not always existed. If the universe had a beginning, and if light traveled at a measurable speed, then there must be a calculable boundary beyond which no light could yet have reached us. If we knew the moment of creation, he wrote, we should be able to calculate its boundary. Mädler was the first to put the pieces together in a scientific framework. His solution was qualitative, not mathematical, but it pointed in the right direction. According to the historian Edward Harrison, the first mathematically satisfactory resolution was published by Lord Kelvin in 1901, in a little-known paper combining finite stellar age with finite speed of light. Kelvin derived the relationship. He showed that if stars had existed for only a finite duration, and if light traveled at a constant speed, then the sky must be dark beyond a certain threshold. He was unaware of Mädler's work. His resolution was later popularized by Harlow Shapley and became the standard answer taught in textbooks for decades. Whether Mädler or Kelvin deserves credit is a matter of interpretation. Both arrived at the same conclusion. Both understood that the darkness was a signature of time. Both saw that the night sky was dark not because the universe lacked light, but because it lacked the infinite duration required to fill the sky with it. But none of these solutions could take hold until the foundational assumption itself was overturned. The riddle resisted solution for 300 years, not because astronomers were careless, not because the mathematics were too difficult, but because every proposed answer implicitly preserved the assumption of an eternal universe. Dust absorption, spatial truncation, finite stellar lifetimes. All of these could be framed in different ways, supported by different lines of reasoning. But they all left the cosmos fundamentally timeless. They all assumed that the universe had always existed, that it stretched backward into the past without limit. And an eternal universe, no matter how dressed, fills the sky with light. The correct answer required abandoning that assumption entirely. It required accepting that the universe itself had a beginning, that it was not a static stage on which events unfolded, but a dynamic structure with an age, a history, and a future. That acceptance became possible only after Edwin Hubble demonstrated in 1929 that the universe was expanding. Distant galaxies were receding. Space itself was stretching. The redshift of their light revealed motion, and the motion revealed that the cosmos was not eternal, it was young. It had a starting point. And if it had a starting point, then it had not had infinite time to fill the sky. The darkness was not a failure of the cosmos to produce light. It was the signature of a universe with an age. Every wrong answer had been, in its own way, a defense of eternity. A way of preserving the assumption that the universe had always been here, that time was an endless corridor stretching in both directions without boundary. The correct answer was a measurement of time, a recognition that the cosmos had a clock, and that the clock had started ticking at a definable moment in the past. The night sky is dark because the universe is 13.787 billion years old, because light travels at a finite speed, because the stars have not had infinite time to fill the void. The darkness you see tonight is not emptiness. It is the shape of a cosmos, young enough that its farthest edges have not yet sent us their light. It is the boundary of the observable, drawn not by the limits of our instruments, but by the speed of light and the age of everything that exists. The riddle took 3 centuries to solve because the solution required overturning the most deeply held assumption about the nature of existence. That the universe was eternal. That it had always been here. That time stretched backward without limit, without origin, without a moment before which there was nothing. The darkness told us otherwise. And once we learned to read it, the darkness became the most eloquent testimony we have ever received about the structure of the cosmos. It became evidence. It became measurement. It became the signature of a universe that began, that grew, that aged, and that will one day grow darker still. There is a single number that resolves the riddle of the dark night sky. A number measured to within 20 million years, a number that changes everything. The universe is 13,787 million years old, not approximately 14 billion. Not eternal, not infinite in time. The cosmos has a birthday, and we know it with precision. This one fact, measured by the Planck satellite and confirmed across multiple independent observations, dissolves the paradox that unsettled astronomers for 3 centuries. The night sky is dark because stars have not had infinite time to fill it with light. The universe is young enough that the sky has not had time to fill. Light travels at 300,000 kilometers every second, fast enough to circle Earth 7 times in a heartbeat, fast enough to reach the moon in just over a second, the sun in 8 minutes, the nearest star in 4 years. But the universe is so vast, and its age so finite, that most of the stars that exist simply have not had time to send us their light. Not because they are dim, not because something blocks the way, because the signal is still traveling, and the clock has not yet run long enough for it to arrive. Every line of sight that terminates at a star contributes a point of light to the sky. Every line of sight that reaches beyond the farthest star we can see meets only darkness, because the light from anything farther has not yet crossed the distance. The geometry is simple. The consequence is the dark night above you. The universe became transparent 380,000 years after it began. Before that moment, space was filled with a hot plasma of electrons and nuclei, opaque to light, a fog so dense that photons could not travel more than a short distance before scattering. Then the universe cooled, electrons bound to nuclei, atoms formed, and for the first time light could travel freely through space. That first light is still traveling. It arrives today as the cosmic microwave background, a glow released when the universe first became transparent, now stretched by expansion into microwave wavelengths, invisible to the eye, but measurable by instruments, sensitive enough to detect warmth, at 2.72548 degrees above absolute zero. It is the oldest light we can observe. It marks the farthest wall. The boundary is not the edge of the universe. It is the edge of the observable universe, the limit of what light has had time to reach since the beginning. Beyond that boundary, the cosmos continues. Stars burn. Galaxies turn. Structures form in a darkness that is not emptiness, but simply distance beyond the reach of light. The observable universe is a sphere centered on Earth, with a radius of roughly 46.5 billion light-years, not 13.8 billion. The difference is expansion. While light has been traveling for 13.8 billion years, the space it has crossed has been stretching. The source that emitted the light has been receding. By the time the light arrives, the object that sent it lies far farther away than the distance light could travel in a static universe. This is not a contradiction. It is geometry in an expanding cosmos. The light has traveled for 13.8 billion years. The object now lies 46.5 billion light-years distant. Both statements are true, measured in different frames. The cosmic microwave background was released at a redshift of approximately 1100, when the universe was 1,000th of its current size. The region of space that emitted those photons now lies at a comoving distance of roughly 45.7 billion light-years, slightly interior to the full particle horizon. It forms a shell around us, a wall of ancient fire, cooled by expansion into a whisper of microwaves, the last glow of the moment transparency began. What that transparency revealed was not an ocean of light. It revealed the void between the stars. The universe has an age, and that changes everything. The sky has not had time to fill. There is a horizon beyond which no signal can reach us, not because space ends there, but because time has not yet allowed it. The darkness of the night is not a failure of the cosmos to provide light. It is the signature of a universe young enough to still have edges in time. Finite age dominates the explanation. Expansion deepens it. Light that does arrive from the most distant sources arrives redshifted, stretched by the expansion of space into wavelengths longer than the human eye can detect. Ultraviolet becomes visible. Visible becomes infrared. Infrared becomes microwave. The cosmic microwave background itself, radiation that was emitted in the visible and near-infrared range at a temperature of roughly 3000 degrees, arrives today at a temperature barely above absolute zero, in wavelengths measured in millimeters, far beyond the threshold of human vision. Both effects act in the same direction. Finite age means much of the light has not arrived. Expansion means much of the light that has arrived is invisible. Together, they explain why a universe filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, presents a sky that is overwhelmingly dark. The resolution is not that the universe lacks light. The resolution is that the universe has a history. The speed of light is finite. The age of the cosmos is finite. And those two facts together impose a horizon, a boundary not of space but of time, beyond which no light can reach us no matter how many stars burn beyond it. Before this answer became clear, every proposed solution preserved the assumption of an eternal universe. Dust was proposed, absorption, the idea that starlight was somehow swallowed by the medium through which it traveled. But dust in an eternal universe reaches thermal equilibrium with the radiation around it. It absorbs energy and re-emits it. The brightness does not disappear, it changes form. The solution came apart at the level of thermodynamics. Others proposed that the universe is finite in extent, that the stars simply run out at some distance. Mathematically, this truncates the sum. The sky remains dark. But a finite static universe collapses under its own gravity. Without expansion, the solution is unstable. A poet came closer than the astronomers of his generation. Edgar Allan Poe, in a speculative essay published in 1848, argued that the dark voids in the sky could only be explained if light from the most distant stars had not yet had time to reach us. He grasped the finite speed of light as the key, decades before the physics formalized it. The first scientist to publish a solution in the formal literature was Johann Heinrich von Mädler in 1858. He combined the finite speed of light with the hypothesis that stars had not always existed. According to the historian Edward Harrison, the first mathematically satisfactory resolution was published by Lord Kelvin in 1901. But the full cosmological context would not be clear until decades later, after Edwin Hubble demonstrated in 1929 that the universe is expanding. The riddle resisted solution for 300 years, because every proposed answer implicitly preserved eternity. And an eternal universe, no matter how dressed, fills the sky with light. The correct answer required abandoning that assumption. It required accepting that the cosmos has an age, that it began, that it has not always been here. The cosmic microwave background is the direct observational evidence of that beginning. Not the beginning itself, but the earliest light we can observe, released when the universe cooled enough for atoms to form and photons to travel freely for the first time. It is the echo of transparency, the glow of the moment the fog lifted. And what it revealed once the universe became transparent was not brilliance. It revealed the dark. The universe is 13,787,000,000 years old, measured to within 20 million years. That precision signals that we know this number with measured confidence, constrained by observation, by the temperature fluctuations in the cosmic microwave background, by the distribution of galaxies, by the abundances of light elements forged in the first minutes after the beginning. The age is young enough that light from the farthest stars has not yet arrived. Old enough that we can see galaxies formed when the universe was only a few 100 million years old, their light stretched by expansion into infrared wavelengths. The James Webb Space Telescope, operating from a point 1.5 million kilometers from Earth, continues to push deeper into that early darkness, measuring the redshifts of galaxies that formed before the first billion years had passed. But even those first stars did not fill the sky. Even in a universe now nearly 14 billion years old, with hundreds of billions of galaxies scattered across observable space, the night remains dark. Because the universe is vast. Because light has a speed. Because time has a limit. The observable universe extends roughly 46.5 billion light-years in every direction, a sphere whose boundary is defined not by a wall of matter, but by a wall of time. Beyond that boundary, light has not had time to reach us. The cosmos almost certainly continues, possibly infinitely, but we cannot see it. Not because it is hidden, because the signal has not yet arrived. The cosmic microwave background forms the farthest shell we can observe, a surface of last scattering, the moment when photons decoupled from matter and began their journey through transparent space. It is real radiation, the last glow of the plasma epoch, arriving today at a temperature of 2.72548 Kelvin, a whisper of warmth in the microwave range, invisible to the eye but filling every cubic centimeter of space. That glow is uniform to within 1 part in 100,000. The tiny fluctuations in its temperature map the density variations in the early universe, the seeds from which galaxies and galaxy clusters would later grow. The cosmic microwave background is a photograph of the universe at 380,000 years old, a snapshot of the cosmos before the first star had formed, when space was still smooth and nearly featureless. What came after was structure. Gravity pulled matter together, the first stars ignited, galaxies assembled, the universe filled with light, but that light has been traveling ever since, and most of it has not yet reached us, or has been stretched by expansion into wavelengths we cannot see. The darkness of the night sky is not the absence of light sources. It is the consequence of a universe with an age. A universe young enough that the sky has not had time to fill. A universe expanding fast enough that much of the light that does arrive is redshifted beyond the visible range. The resolution is layered. Finite age explains why much of the light has not arrived. Expansion explains why much of the light that has arrived is invisible. Darkness is not one thing. It is the sum of multiple physical facts, each contributing to the same observable consequence. The universe has an age. That age is finite. And because it is finite, the night is dark. This is not a lack, it is a signature. The darkness tells us the universe has a history. It tells us light has a speed. It tells us time has a shape. The dark sky is not a void. It is a message, written in the absence of photons, carrying information about the structure of space-time, the constitution of matter, the trajectory of cosmic expansion. When you look into the night, you are looking at a boundary imposed by the speed of light and the finite age of the universe. You are looking at the limit of what can be known from observation, the edge of the observable cosmos, beyond which the universe continues in a darkness that is not absence but simply distance beyond the reach of light. The universe became transparent, and what transparency revealed was the void between the stars. The first light traveled. The cosmic microwave background was released. Galaxies formed. Stars ignited. And still the sky remained dark. Because the universe was young. Because space was expanding. Because time had not yet run long enough for every signal to arrive. The answer took 3 centuries to find because it required abandoning the assumption of eternity. It required accepting that the universe has an age, that it began, that it has not always been here. And once that assumption was abandoned, the darkness made sense. It was no longer a paradox, it was a prediction. The night sky is dark because the universe is 13,787,000,000 years old. Because light travels at 300,000 kilometers per second. Because the observable universe has a radius of 46.5 billion light-years. Because the cosmic microwave background marks the farthest wall we can see. Because expansion stretches light into invisibility. The darkness is not emptiness. It is the shape of a cosmos with an age, with boundaries in time, with a history written in the absence of light. The riddle that unsettled astronomers for 3 centuries is resolved. The answer is not absence. The answer is youth. The universe has not had time to fill the sky. And in that darkness measured and understood you rest. Space itself stretches, and light traveling through it stretches with it. This is not a metaphor. It is a physical process, measured and mapped, that transforms the visible into the invisible across the longest distances in the universe. When a photon leaves a distant galaxy and begins its journey toward us, it carries a wavelength, determined by the atom that emitted it. But as the photon crosses the expanding cosmos, the fabric of space through which it moves is itself growing. The wavelength grows with it. What began as blue light becomes green, then red, then infrared, then microwave. The light does not fade, it simply shifts beyond the range our eyes were built to detect. This is cosmological redshift. It is not the Doppler effect, though the two are often confused. The Doppler effect describes motion through space changing the color of light. Cosmological redshift is different. The galaxies are not moving through space away from us in the ordinary sense. Space itself is expanding. and the light stretches because the medium it travels through is stretching. The farther the light has traveled, the more space has expanded beneath it, and the more profoundly it has been redshifted. At a redshift of 1, the wavelength has doubled. A photon that left its source as violet arrives as deep red. At a redshift of 7, the wavelength has multiplied by 8. Ultraviolet becomes infrared. Visible light becomes invisible. The visible spectrum occupies a narrow band, wavelengths between roughly 380 and 700 nanometers. Anything shorter is ultraviolet. Anything longer is infrared. Our eyes are tuned to this slice of the electromagnetic spectrum because it is the slice that penetrates Earth's atmosphere and reaches the surface where life evolved. But the universe does not care what our eyes can see. Most of its light arrives in wavelengths we cannot perceive. A galaxy 10 billion light-years away emits light across the full spectrum. But by the time that light reaches us, the expansion of space has stretched every wavelength. The ultraviolet has shifted into the visible range. The visible has shifted into the infrared. The infrared has shifted into microwaves. We can still detect the light with instruments, but to the unaided human eye, the galaxy is invisible. Not because it is faint, though distance does dim it, but because its light has been stretched into wavelengths our retinas cannot register. The most extreme example we have is the cosmic microwave background. This is the oldest light in the universe, radiation released when the cosmos was 380,000 years old, when electrons first bound to nuclei and photons could travel freely for the first time. At the moment of release, this light had a temperature of roughly 3,000 degrees above absolute zero. It glowed in the visible and near-infrared range, a warm orange radiance filling all of space, but that was 13.8 billion years ago. Since then, space has expanded by a factor of roughly 1100. The wavelength of every photon in that ancient glow has been stretched by the same factor. What began as visible light now arrives as microwave radiation, with a temperature of 2.7 degrees above absolute zero. It fills the sky uniformly in every direction, but you cannot see it. You can only measure it. The cosmic microwave background is the signature of a universe that has aged and expanded so profoundly that its first light has been stretched into invisibility. This is not a loss, it is a transformation. The light is still there, instruments detect it, radio telescopes map it. Satellites measure its temperature fluctuations to 5 decimal places, but to the human eye, it is darkness. Even if we could gather all the light emitted by every galaxy in the observable universe, most of that light would arrive redshifted beyond the visible range. The cosmic optical background is the name given to the total amount of light in optical wavelengths that reaches us from all sources throughout cosmic history. It has been measured. In 2021, NASA's New Horizons spacecraft, traveling beyond the orbit of Pluto, where the zodiacal light and scattered glow of the inner solar system no longer interfere, pointed its camera at the darkest patches of sky it could find, and measured the faint glow that remained. The result was a number so small, it barely registers on any human scale of brightness. Roughly 16 nanowatts per square meter per steradian, at a wavelength near 600 nanometers. That is the sum total of all the optical light from all the galaxies in the universe, integrated across billions of years of cosmic history, arriving at Earth. It is so faint that even in the darkest skies far from any city, the human eye cannot distinguish it from perfect blackness. For a brief time, astronomers wondered whether the measured brightness was larger than expected. whether there might be an unknown component not accounted for by the known population of galaxies. Measurements that puzzled astronomers. But a later, more careful analysis largely resolved the discrepancy. The light we measure is consistent with the light we expect from the galaxies we know. The conclusion is inescapable. The universe is not dark because it lacks light. It is dark because most of its light has been stretched beyond what our eyes were built to see. Finite age explains why the sky is not filled with an infinite blaze of stars. But expansion deepens the darkness. Even the light that does reach us from distant galaxies arrives transformed, shifted into wavelengths our biology cannot register. You are standing under a sky filled with light you cannot see. Infrared, microwave, radio. The galaxies are there. The stars are burning. The photons are arriving. But the expansion of space has carried them beyond visibility. What appears to you as an empty void is in fact a cosmos blazing in frequencies your eyes were never designed to detect. This is the fourth answer to the riddle of the dark night. The first was that the universe has an age. The third was that the universe became transparent, and what transparency revealed was the void between the light sources. But this fourth answer is subtler. Even the light that has had time to reach us arrives mostly invisible. Redshift is not the primary cause of the darkness. That honor belongs to finite age. But redshift ensures that the darkness is deeper than it would otherwise be. The night sky is a record of expansion. Every photon that reaches your eye has traveled through a universe that was smaller when the photon began its journey than it is now. The farther the photon has come, the more space has grown, and the more its wavelength has stretched. The darkness you see is not emptiness. It is the consequence of a cosmos in motion, a universe whose very fabric is pulling apart, carrying light with it into ranges beyond human perception. There is no dread in this. Only structure. The stretching of light is not a loss but a signature, a way the universe writes its history into the radiation that crosses it. When you look up tonight and see darkness, you are seeing the shape of cosmic expansion made visible. Or rather, made invisible. The darkness is the mark of a universe that has stretched for 13.8 billion years, and will continue stretching long after the last human eye has closed. The light is still there, it has simply been carried beyond you. And the sky remains dark, not because the universe is empty, but because it is vast, old, and moving, and because your eyes, evolved on the surface of a warm planet orbiting a middle-aged star, were built to see only the narrow slice of radiation that happened to be useful for survival. The rest of the spectrum passes over you in silence, undetected, filling the night with a light you will never see. This is not the end of the answer, it is one rung. The darkness has more to say. But for now, let the image settle. Space stretches, light stretches with it, and the sky, filled with invisible fire, remains dark. Beyond the farthest galaxies there is a boundary, not the edge of the universe itself, but the edge of what we can observe. A sphere centered on Earth, reaching outward to a distance of 46.5 billion light-years in every direction. The particle horizon. The limit of light's journey since the beginning, this is not the distance light has traveled. Space itself expanded while the light was in flight, carrying the sources away, even as their photons crossed the void toward us. The commoving distance, the actual separation today between us and the region that emitted the oldest light, stretches far beyond any simple calculation. 46.5 billion light-years. A number that sounds impossible until you remember that space itself has been stretching, carrying everything with it. And at that boundary we do not find a galaxy, we do not find a star, we find something older than both. A wall of ancient fire. The cosmic microwave background. Radiation released when the universe was 380,000 years old, when it cooled enough for electrons to bind to atomic nuclei and photons could travel freely for the first time. Before that moment, the universe was opaque, a dense fog of plasma where light scattered endlessly. After that moment, the universe became transparent. The photons released in that transition have been traveling ever since, crossing an expanding cosmos, redshifting as space stretched, arriving today as a faint glow at 2.72548 degrees above absolute zero. This is the farthest wall we can observe, not because there is nothing beyond it, but because light from anything beyond has not yet had time to reach us. The region of space that emitted those photons now lies at a comoving distance of roughly 45.7 billion light-years, slightly interior to the full particle horizon. A wall of radiation, ancient and cold, surrounding us in every direction. It was not always cold. When it was released, the background had a temperature of roughly 3,000 degrees, glowing like the surface of a dim red star. But the universe has expanded by a factor of more than 1,000 since then, stretching every wavelength, cooling the radiation until it became invisible to human eyes. What was once a wall of fire is now a whisper of warmth, detectable only by instruments tuned to microwaves, to wavelengths measured in millimeters. The background is the most extreme example of cosmological redshift we can observe. Light that began in the visible spectrum, stretched across 13.8 billion years of expansion, arriving today in a form we cannot see without technology. The darkness of the night sky includes this radiation. It surrounds you, passes through you, fills every cubic centimeter of space with roughly 400 photons, and you cannot perceive a single one, not because they are absent, because they have been stretched beyond the range your eyes were built to detect. This is the signature of a universe with an age. The background is both evidence of the boundary and evidence of the expansion, the oldest light in the universe, and it is dark. But there is another horizon, one that points not to the past, but to the future. The particle horizon describes what we can see now, the maximum distance from which light has had time to reach us since the Big Bang. The cosmic event horizon describes what we will ever be able to see, the maximum distance from which light emitted today can reach us in the future. And these two horizons are not the same. The event horizon lies at a comoving distance of roughly 16 billion light-years, closer than the particle horizon, smaller. This is the consequence of dark energy. The accelerating expansion, driven by a property of space itself that we do not yet understand, means that galaxies currently within our observable universe are continuously crossing the event horizon. Not because they are moving, because the space between us expands faster than light can cross it. A galaxy that crosses the event horizon does not disappear instantly. Its light continues to arrive, but the light we receive will have been emitted progressively, earlier in the galaxy's history. If our current understanding holds, high redshift sources will eventually freeze on a fixed moment in their evolution, their light redshifting beyond detection, fading into silence. Not because the galaxy stops shining, because the space between us expands faster than new light can cross the gap. They slip beyond the horizon, their last light frozen in time, stretched into wavelengths so long they become indistinguishable from the hum of space itself. The darkness beyond the particle horizon is not emptiness. It is cosmos that exists but whose light has not yet arrived, or will never arrive. Stars burn there, galaxies turn. Structures form, and collapse, and reform. But their light has not had time to cross the space between us, or the expansion has carried them beyond the reach of any signal they could send. The boundary is not a wall in space, it is a wall in time. A limit imposed by the speed of light and the finite age of the universe, 46.5 billion light-years. A sphere centered on Earth, not because Earth is special, but because every observer sits at the center of their own observable universe. An astronomer in a galaxy 10 billion light-years from here would see a different particle horizon, a different set of galaxies at the edge of visibility. The boundary moves with the observer. It is not a feature of the universe, it is a feature of observation itself. And at that boundary we see not the present but the past. The light from the background left its source when the universe was 380,000 years old. It has been traveling for 13.8 billion years. We do not see the region as it is now. We see it as it was then, a glowing plasma cooling into transparency, releasing the first free photons into a universe that had just become capable of letting them pass. If we could somehow travel to that region today, instantaneously, we would not find the glowing plasma. We would find galaxies, stars, perhaps planets, structures that formed over billions of years after the light we observe was emitted. But we cannot see those structures. The light they emit now will never reach us. The expansion has carried them beyond the event horizon. They exist in a region of the universe that is real, physical, full of matter and energy, and completely inaccessible to observation. The background is the farthest edge of the visible past. Beyond it there is no light that can reach us, not because the universe ends there, because transparency began there. Before the moment electrons and nuclei bound together, the universe was opaque. There is no image, no photon, no electromagnetic signal that can reach us from before that moment. The background is the wall where observation ends and inference begins. But it is not a wall of nothing, it is a wall of radiation. Real photons carrying real energy, arriving from real regions of space, the oldest light in the universe, surrounding us in a shell, a sphere of ancient fire cooled to 2.7 degrees above absolute zero. Invisible, but measurable. Dark, but not absent. The darkness of the night sky includes this boundary. It includes the light that has not yet arrived. It includes the galaxies slipping beyond the event horizon, their signals stretching into silence. It includes the background, the faint glow that fills the sky in every direction, undetectable to your eyes but present in every measurement, every map, every image of the cosmos at its largest scale. You are inside the observable universe. You are sitting near the center of a sphere, 46.5 billion light-years in radius, surrounded by a wall of ancient fire that you cannot see, watching galaxies slip beyond a horizon you cannot cross. The boundary is not far away in the sense of being unreachable by travel. It is far away in the sense of being unreachable by light. And light is the only messenger we have. Beyond that boundary, the universe continues. Stars burn. Galaxies collide. Clouds of gas collapse into new generations of stars, and old stars explode and seed the void with heavy elements. All of it happening in a darkness that is not emptiness but simply distance beyond the reach of light. Between September of 2003 and January of 2004, the Hubble Space Telescope turned toward a patch of sky in the constellation Fornax that appeared, to every instrument that had looked before, empty. Not empty the way a desert is empty. Empty the way a void is empty. No visible stars. No galaxies bright enough to register. A rectangle of sky roughly 1/10 the angular diameter of the full moon. A grain of sand held at arm's length would cover more area. Hubble pointed there anyway and held its gaze for 400 orbits, 800 exposures, 11 1/3 days of total exposure time. What came back was not emptiness. What came back was nearly 10,000 galaxies. The image released in March of 2004 carried the name Hubble Ultra Deep Field. Where the sky had appeared empty, Hubble found it full. Not full of stars, but full of entire universes. Nearly every point of light in the frame is a galaxy containing billions of stars, lying billions of light-years away. The few stars visible, perhaps 7 in total, belong to our own Milky Way. You can identify them by their diffraction spikes, the cross-shaped flare a point source makes in the optics. Everything else, every smudge and spiral and elliptical glow, is an island of hundreds of billions of suns. So distant the light now arriving left those shores 400 million to 800 million years after the Big Bang. The ultra-deep field was, at the time of its release, the deepest visible light image of the universe ever obtained. It has since been surpassed, first by the Hubble Extreme Deep Field in 2012, which combined 10 years of data and reached further back, and later by images from the James Webb Space Telescope, which sees in infrared and peers through dust and redshift into epochs Hubble could not reach. But the ultra-deep field remains the image that taught us how to count the dark. Because if a patch of sky 1/26 millionth the area of the entire celestial sphere contains 10,000 galaxies, the question becomes unavoidable. How many galaxies fill the whole sky? The arithmetic is simple in principle. Multiply the count by the coverage. Assume the universe is roughly uniform on the largest scales. Extrapolate. The number you arrive at is somewhere between hundreds of billions and 2 trillion galaxies in the observable universe. The exact figure is still debated. One analysis in 2016 suggested 2 trillion, arguing that 90% of galaxies are too faint to detect. Another in 2021, using measurements from New Horizons at the outer edge of the solar system, concluded the number is more consistent with hundreds of billions. The tension has not been resolved. But in a sense, the difference barely matters to the imagination. Both numbers are so large the mind cannot hold them as quantities, only as symbols of vastness. What matters is the implication. The universe is dense with galaxies, each a system of hundreds of billions of stars, and nearly all invisible to the unaided eye, most invisible even to the largest telescopes, unless you point at the darkness and wait. The ultra-deep field taught us that what we call empty sky is not empty. It is full of light that has traveled so far it arrives as the faintest whisper, a few photons per square meter per second, accumulated over days to become visible at all. Darkness is not the absence of sources. Darkness is the consequence of distance, of dilution, of the inverse square law applied across billions of light-years. Every galaxy in that field is radiating. Every star is pouring photons into space. But by the time that light crosses the gulf, it has spread thin, red-shifted into the infrared, and the night sky remains dark. And it taught us something else. We live in a universe where the sky has not yet had time to fill. The sum total of all optical light from all galaxies across cosmic history is called the cosmic optical background. New Horizons measured it in 2021 from beyond Pluto, far enough from the Sun to see the faint glow of the universe itself. The measurement came back at roughly 16 nanowatts per square meter per steradian, at a wavelength of 608 nanometers. An extraordinarily faint glow. The daytime sky on Earth is roughly 10 billion times brighter. The cosmic optical background is so dim you would never notice it, drowned out by airglow, zodiacal light, scattered city glow, the Milky Way itself. But it is there. Real. The accumulated light of every galaxy that has ever shone, arriving as a glow so faint it can only be detected from the outer solar system, looking back with instruments sensitive enough to measure the difference between near total darkness and the faintest possible illumination. And even that glow is mostly invisible to human eyes. redshifted out of the visible range into infrared and microwaves by the expansion of space. The ultra-deep field is a portrait of that glow, concentrated and made visible by the patience of a telescope that stared long enough to let photons accumulate. A portrait of a universe full of light, but young enough and vast enough that the light has not yet filled the sky. A portrait of the answer to the riddle that unsettled astronomers for 3 centuries. The sky is dark not because the universe lacks stars, but because the universe has an age, and light has a speed, and together they mean there has not been enough time for every star in every galaxy to send us its light. 10,000 galaxies in a patch the size of a sand grain at arm's length have sent us their light, and we have caught it. But most of the universe remains beyond the horizon, not because it does not exist, but because its light has not yet had time to arrive. In 2012, Hubble returned to the same field and stared longer. The extreme deep field combined a decade of observations, reaching galaxies that existed just 450 million years after the Big Bang. It covers roughly 2.3 by 2 arc-minutes and contains about 5,500 galaxies. Some are so distant their light has traveled 13.2 billion years. They appear not as spirals but as faint red smudges, their light stretched by expansion to wavelengths at the edge of what Hubble can detect. They are among the first galaxies ever to form, lighting up in a universe that had been dark for hundreds of millions of years after the cosmic microwave background faded, before the first stars had ignited in sufficient numbers to reionize the hydrogen filling space. The extreme deep field is not a replacement, it is a continuation of the same experiment, the same question asked with more patience. What is out there in the dark? And the answer every time is more. More galaxies, more light, more history, more time compressed into a single image, because every galaxy exists at a different epoch, a different distance, a different moment. The light from the nearest left a few 100 million years ago. The light from the farthest left more than 13 billion years ago, when the universe was less than 1/20th its current age. To look at the extreme deep field is to see time laid out in layers, each galaxy a window into a different era, all arriving simultaneously, piling up photon by photon into an image containing more cosmic history than any human eye could perceive in a lifetime of looking up. And still, the night sky is dark. Even with hundreds of billions of galaxies, even with every star radiating across the electromagnetic spectrum, the light reaching us is so diluted by distance, so redshifted by expansion, so young in the context of cosmic time, that it does not fill the sky. The darkness remains, not as emptiness, but as the space between sources. Not as absence, but as distance. Not as void, but as the signature of a universe vast enough and young enough that light has not yet had time to reach us from every corner. The ultra-deep field and the extreme deep field are experiments in counting the dark. They are maps of how much light exists in a universe that appears dark, and they are proof the appearance is not illusion but consequence. The sky is dark because the universe is finite in age, because light travels at a fixed speed, because space expands and stretches the light crossing it. The darkness you see tonight is not empty. It is full of galaxies we have only begun to count, full of light that has not yet arrived, full of distances so vast that even 10,000 island universes in a patch smaller than a sand grain cannot fill the sky. And somewhere, right now, the James Webb Space Telescope floats at the second Lagrange point, 1.5 million kilometers from Earth, continuing what Hubble began, pointing into the cosmic dark, capturing galaxies even Hubble could not see, extending the count deeper, further back in time, toward the darkness that preceded all stars. The experiment continues. The sky remains dark, and the darkness has a measure. We have counted the stars, traced the light, measured the horizon. We have seen that darkness is not simply absence, but the signature of a universe, with boundaries, and a beginning. And now we arrive at the deepest layer. Most of the universe does not emit light. Not because it is too far away, not because its light has been stretched into invisibility, but because it is made of substances that cannot emit light at all. According to measurements taken by the Planck satellite and published in 2020, ordinary matter, the kind that forms stars and planets and gas and dust and human beings, constitutes just 4.9% of the energy content of the universe. Dark matter accounts for 26.8%. Dark energy accounts for 68.3%. Together they make up 95.1% of everything that exists. And none of it emits, absorbs, or reflects electromagnetic radiation in any currently detectable form. The darkness of the night sky is not the absence of light sources. It is the consequence of a universe composed mostly of things that cannot make light. Dark matter does not interact with light at all. It passes through electromagnetic radiation as if it were not there. Dark matter does not emit visible light, does not glow in infrared, does not whisper in radio waves, does not flare in X-rays. It interacts with gravity and gravity alone. Its existence was first proposed in 1933 by Fritz Zwicky, studying the motion of galaxies in the Coma cluster. Galaxies were moving far too quickly to be held together by the gravity of their visible matter alone. Something unseen was holding them in place. Decades later, in the 1970s, Vera Rubin and Kent Ford confirmed the same phenomenon independently, measuring the rotation curves of spiral galaxies. Stars at the outer edges orbit at velocities that should fling them into intergalactic space if only visible matter were present. Yet they remain, bound by the gravity of something that emits no light. The rotation curves stay flat, far beyond the visible disk, tracing the outline of vast halos of dark matter surrounding every galaxy like invisible scaffolding. Dark matter has mass. It collapses into structures. It forms halos around galaxies, filaments between clusters, the cosmic web itself. It holds the universe together at the largest scales, and it is completely dark. Dark energy is something else entirely. It is not matter at all. It does not have mass in the ordinary sense. It does not collapse into structures. It is a property of space itself, possibly a form of vacuum energy, associated with Einstein's cosmological constant. The more space there is, the more dark energy there is, and the faster the expansion of the universe accelerates. Dark energy was discovered in 1998 by two independent teams observing distant Type Ia supernovae. These supernovae, exploding white dwarf stars, serve as standard candles, their brightness calibrated by their light curves. The teams expected to measure a universe whose expansion was slowing under the pull of gravity. Instead, they found that distant supernovae were receding more slowly than expected for their redshift, which could only mean one thing: the expansion of the universe is not slowing. It is accelerating. The discovery earned the Nobel Prize in Physics in 2011. And it revealed that the dominant component of the universe is something we do not understand at all. Dark energy does not clump, does not attract, does not hold anything together. It acts in opposition to gravity at cosmological scales, pulling space apart, driving galaxies away from one another at an ever-increasing rate. Its fundamental nature is completely unknown. Two darknesses, one that holds galaxies together, one that tears the universe apart, both invisible, both dominant, neither understood. The word dark is used for both, but it is a terminological coincidence, not a shared property. Dark matter does not interact with electromagnetism, but does interact with gravity. It has mass, forms structures, collapses into halos. Dark energy has no detectable mass, forms no structures, and acts in opposition to gravity at cosmological scales. They are dark for physically distinct reasons. One is a substance, the other is a property of the void. We built our entire understanding of the cosmos from 5% of what exists. The other 95% has been there all along, shaping everything, untouched by light. Every galaxy we observe is embedded in a halo of dark matter, 10 times more massive than the visible stars. Every measurement of cosmic expansion is dominated by dark energy, accelerating the separation of structures across billions of light-years. The light we see, the stars we count, the galaxies we photograph, are traces of a much larger architecture, one that emits nothing. The night sky is dark, not only because the universe is young, not only because it is expanding, but because most of it is made of things that cannot shine. The darkness is not a gap in the data, it is the data. It is the majority state of the cosmos, the structural foundation upon which the visible universe rests. Dark matter was inferred from motion. Zwicky saw galaxies moving too fast. Rubin saw stars orbiting too quickly. The light told them where to look, but the light itself was not the answer. The answer was in the gravity, in the pull of something that could not be seen. Every spiral galaxy is a lighthouse surrounded by an invisible continent. Every cluster of galaxies is held together by a web of dark matter filaments stretching across millions of light-years, traced only by the gravitational lensing of background light. Dark energy was inferred from distance. The supernovae were too faint for their redshift, which meant they were farther away than expected, which meant space had expanded more than it should have if gravity alone were in control. The light arrived, but it arrived from a universe that was accelerating away. The expansion that redshifts distant galaxies into invisibility is itself driven by a component of the universe that emits nothing, absorbs nothing, reflects nothing. The darkness is not empty, it is full of dark matter, full of dark energy, full of structures and forces that shape the cosmos without ever producing a single photon. Ordinary matter, the kind that makes stars and planets and light, is the exception. It is the thin, luminous skin on a body made mostly of darkness. The stars are islands. The galaxies are sparks. The cosmic web of visible matter traces the outline of a much larger web of dark matter, like frost on a window, revealing the shape of the glass beneath. And the window is expanding. Dark energy ensures that the more space there is, the faster it pulls apart. Galaxies currently within our observable universe are continuously crossing the event horizon. The boundary beyond which light emitted today will never reach us, no matter how long we wait. Not because they switch off, but because the space between us expands faster than light. They slip beyond the horizon, their last light frozen in time, redshifting into silence. The Planck satellite measured the composition of the universe with extraordinary precision. 4.9% ordinary matter, 26.8% dark matter, 68.3% dark energy. The precision signals that we know this distribution with measured confidence, that the darkness has been weighed and catalogued, that the invisible has been mapped by its effects. The cosmic microwave background, the oldest light we can observe, carries within its temperature fluctuations the imprint of dark matter. The slight variations in temperature trace the density fluctuations in the early universe, the seeds from which galaxies grew. Those seeds were planted by dark matter. The ordinary matter followed, falling into the gravitational wells that dark matter had already carved. The light we see in the cosmic microwave background is the echo of a process driven mostly by things that emit no light. Dark matter shaped the universe before the first stars ignited. Dark energy will shape it long after the last stars fade. The universe spent its first few 100,000 years in complete darkness before recombination released the cosmic microwave background. It will spend its last trillion years, and then a Google more, in complete darkness, after the last stars die and the last black holes evaporate. The darkness is not the anomalous state of the universe, it is its natural and majority state. Stars are the exception. Light is the exception. We live in the brief flare between two infinite darks, on a planet warmed by a star that is one of trillions, in a galaxy held together by 10 times its mass in dark matter, in a universe accelerating apart under the influence of dark energy. And most of it emits nothing. The night sky is dark because the universe is young, because it is expanding, and because it is made mostly of substances that cannot emit light. Finite age means the sky has not had time to fill. Expansion means the light that does arrive has been stretched into invisibility. And dark matter and dark energy mean that even if every source of light were visible, we would still be observing only 5% of what exists. The darkness is not absence. It is presence, it is the majority, it is the structure, it is the scaffolding on which galaxies hang, the force that pulls them apart, the foundation of everything we see. We do not live in a universe of light interrupted by darkness. We live in a universe of darkness interrupted by light. The visible matter is the thinnest thread woven through a fabric made mostly of things that do not shine. And the thread is beautiful precisely because it is rare. Dark matter does not glow, but it holds the Milky Way together. Dark energy does not radiate, but it will determine the fate of every galaxy in the observable universe. The darkness is not inert, it is active, structural, dominant. It shapes the motion of stars, the formation of galaxies, the expansion of space itself. Dark matter and dark energy are not mysteries in the sense of being unknowable. They are mysteries in the sense of being known only by their effects. We know how much dark matter there is. We know how it clusters, how it shapes galaxies, how it bends light. We know how much dark energy there is. We know how it accelerates expansion, how it determines the fate of the cosmos. We do not know what either of them is. And that is not a failure. It is the current edge of knowledge. The darkness has been measured. It has been weighed. It has been mapped. What remains is to understand it. You are not sleeping under an empty sky. You are sleeping under a sky full of dark matter, under the influence of dark energy, under the light of stars that make up 5% of the universe. The other 95% is there, shaping the motion of the Milky Way, pulling distant galaxies beyond the horizon, holding the cosmic web together even as space expands. The darkness is not a void, it is the majority, it is the foundation, it is the architecture of the cosmos, invisible but present, shaping everything, emitting nothing. And it is what makes the night sky dark. We live at the midpoint of the age of stars. The universe is not young. Not in the early morning of creation, but approximately halfway through the only era in which energy is generated by the birth, life, and death of stars. This is called the stelliferous era, a span that began when the first hydrogen clouds collapsed into fusion, and will end when the last ember fades. We are here, now, in the middle of that brief brightness. The stars will not burn forever. The last to die will be the dimmest ones, the red dwarfs, barely glowing, hoarding their hydrogen for trillions of years. They are the smallest stars, less than half the mass of the Sun, burning so slowly that some will survive 100 trillion years. When galaxies exhaust their hydrogen gas and star formation ceases, these faint red embers will be all that remains. And when the last one fades, the universe will be 10,000 times older than it is today. 100 trillion years from now, the sky will hold no ordinary stars. What follows is called the degenerate era, a name that carries no judgment, only description. The universe will be dominated by white dwarfs, brown dwarfs, neutron stars, and black holes. No light from ordinary stars will illuminate any sky. The cosmos will be colder, darker, and more diffuse. This is not the end of the universe, only the end of the brief age in which stars were common. The white dwarfs will cool slowly, radiating their stored heat into the expanding void. They are the cores of stars like the Sun, compressed to the density of a teaspoon of matter weighing a ton, glowing faintly from residual warmth. Over trillions of years they will dim from white to red to black, becoming cold spheres of carbon and oxygen drifting through space that no longer remembers them. Brown dwarfs, never massive enough to sustain fusion, will cool alongside them. Neutron stars, the collapsed cores of massive stars, will spin in silence, their magnetic fields decaying, their surfaces cooling toward absolute zero. The universe will not be empty, but it will be dark in a way no living eye has ever witnessed. And the black holes will remain. For a time. Black holes, according to our current understanding of quantum physics, eventually evaporate. Stephen Hawking predicted in 1974 that black holes emit radiation, a quantum process so slow it has never been directly detected for any astrophysical object. A black hole with the mass of the Sun would take a number of years written with 67 digits to evaporate. Supermassive black holes at the centers of galaxies, millions or billions of times more massive, would take a number of years, written with nearly 100 digits. This is the slowest known process in the universe. But if the mathematics holds, if the quantum fields behave as we believe they do, then even the black holes will eventually dissolve. They will shrink, atom by atom, photon by photon, radiating their mass back into the void as faint warmth, until the last one vanishes and leaves behind only the ghost of its gravitational well, smoothing into the fabric of space. What remains after that is called the dark era. The universe will consist of photons, neutrinos, electrons, positrons, and sparse radiation dispersed through eternally expanding space. No stars. No galaxies. No structures of any kind. The temperature will approach absolute zero, not because the universe has died, but because it has emptied. Space will continue expanding, carrying the remnants farther apart, diluting the already vanishing density of matter and energy into a silence that stretches without limit. The universe does not die, it empties, cools, and darkens, expanding forever into a silence that has no witnesses. This far future is not speculation in the sense of fantasy. It is the logical consequence of physical laws we can measure today, extrapolated forward through timescales that dwarf the entire history of stars. The stelliferous era, the age in which we live, spans from roughly 1 million years after the Big Bang to 100 trillion years. The degenerate era that follows lasts from 100 trillion years to a number so large it requires scientific notation to express, written as 10 to the power of 37. And the dark era that follows lasts longer still. If you imagine the entire history of the universe as a book, the age of stars occupies a few pages near the beginning. The rest is darkness, measured in chapters so long that the word forever begins to lose its metaphorical weight and becomes a physical description. The darkness of tonight's sky is a preview, not of emptiness but of the universe at rest. The night sky is dark now because the universe is young enough that light from the most distant stars has not yet had time to arrive, and because the universe is expanding fast enough that much of the light that does arrive has been stretched into wavelengths we cannot see. But in the far future, the sky will be dark for a simpler reason. There will be no stars left to emit light in the first place. The red dwarfs will fade one by one, their hydrogen exhausted, their cores cooling into darkness. The white dwarfs will radiate their last warmth into space that no longer holds anything warm enough to receive it. The black holes will evaporate over timescales so vast that the entire stelliferous era, all 100 trillion years of it, will seem like a brief flicker in comparison. And when the last black hole dissolves, the universe will enter a state it will never leave, cold, dark, and expanding, with no process remaining that can generate light. This is not a tragedy, it is not a failure. It is simply the shape the universe takes when all available energy has been radiated away, when all structures have dissolved, when the only motion left is the expansion of space itself, carrying the remnants farther apart into a dispersal that has no end. The cosmos spent its first few 100,000 years in complete darkness before the first stars ignited. It will spend its last googol of years in complete darkness after the last black holes evaporate. The age of stars, the age we are living through, is an infinitesimal fraction of the total duration, a brief flare in a darkness that came before and will return. And yet we are here, now, in the middle of it. The sun will continue to rise for billions of years. The stars will continue to burn for trillions. The night sky will remain dark, not because the universe is empty, but because it is young, because it is expanding, because most of its substance emits no light. The darkness is not a void. It is the signature of a universe with an age, with a constitution, with a history that we can measure and describe. You are not sleeping under an empty sky. You are sleeping under the oldest light in the universe, under a darkness that has a name, a measurement, a history. The red dwarfs are still burning. The white dwarfs are still warm. The black holes are still here, holding the centers of galaxies, radiating nothing, patient beyond comprehension. The far future will come, but it is not here yet. Tonight, the sky is dark, because the universe has had just enough time to become something. Just enough time for hydrogen to collapse into stars, for stars to fuse carbon and oxygen and iron, for planets to form, for warmth to gather in small pockets against the cold. The darkness surrounds all of it, but it does not erase it. Not yet. And for now, that is enough. The darkness of tonight's sky is not emptiness. It is the signature of a universe with an age, a history, and a constitution. The riddle that unsettled astronomers for 3 centuries has finally been answered, and the answer reveals something deeper than the question ever suggested. The night sky is dark because the universe is young, because it is expanding, and because most of what it contains emits no light at all. 13.787 billion years. That is the age of the universe, measured with a precision that would have astonished the astronomers who first posed the riddle. Not infinite. Not eternal. Young enough that light from the most distant stars has not had time to fill the sky. Young enough that darkness still has room to exist between the scattered islands of light. Every line of sight does not terminate at the surface of a star. The logic that predicted a sky as bright as the sun was sound. The assumption beneath it was wrong. The universe has not had infinite time. Stars have not always existed. And the fabric of space itself has been stretching since the beginning, carrying distant sources away faster than their light can close the distance. The expansion stretches that light as it travels. Photons that left distant galaxies in the ultraviolet arrive today in the infrared, invisible to human eyes. The cosmic microwave background, the oldest light in the universe, was released as a glow at 3000 degrees, when the universe first became transparent. It arrives today at 2.72548 degrees above absolute zero, a whisper in the microwave range, undetectable without instruments. The sky is full of light we cannot see. At redshift 1, the wavelength has doubled. At redshift 7, it has multiplied by 8. The farthest galaxies observed by the James Webb Space Telescope emit light that has been traveling for more than 13 billion years. Arriving today shifted so far into the infrared that no human eye could ever register their glow. The universe radiates, but most of that radiation has been pulled beyond the narrow band of frequencies we call visible. And then there is the composition. 4.9% of the universe is ordinary matter, the substance of stars and planets and everything we have ever touched. 26.8% is dark matter, which does not interact with light at all. It does not emit, it does not absorb, it does not reflect. Its existence is inferred exclusively from gravity, from the way galaxies rotate too fast to be held together by visible matter alone, from the way clusters bend light around masses we cannot see. 68.3% is dark energy, not matter at all but a property of space itself. It was discovered in 1998 by observing distant supernovae, receding more slowly than expected, proof that the expansion of the universe is accelerating. The more space there is, the more dark energy there is, and the faster the expansion accelerates. It does not clump, it does not collapse. It pulls the cosmos apart at scales larger than galaxy clusters. 95.1% of the universe does not emit, absorb, or reflect a single photon. Two darknesses. One that holds galaxies together, one that tears the universe apart, both invisible, both dominant, neither understood. We built our entire understanding of the cosmos from 5% of what exists. The other 95% has been there all along, shaping everything, untouched by light. The sky above you tonight contains all of this simultaneously. The particle horizon at 46.5 billion light-years, beyond which light has not had time to arrive. The cosmic microwave background, arriving from a wall of ancient fire released 380,000 years after the Big Bang, the farthest boundary we can observe. The cosmic optical background, 16.37 nanowatts per square meter per steradian, the sum total of all visible light emitted by every galaxy across cosmic history, measured by instruments aboard New Horizons as it drifted beyond the scattered glow of the inner solar system. And the dark matter and dark energy, constituting the vast majority of everything, emitting nothing. Darkness is not simple, it is layered, it is physical, it is measurable. The resolution of the riddle is not that darkness is harmless, it is that darkness has meaning. It is the consequence of comprehensible physical laws, of a measurable cosmic history, of a universe constitution we can describe with precision. The darkness is not a threat, it is the shape of the universe at rest. And you are inside it, on a warm planet, under a sky that is dark precisely because the universe has had enough time to become something. The terror becomes awe, not because the darkness has been explained away, but because it has been understood. The cosmos spent its first 380,000 years in complete darkness, before the first photons could travel freely through space. It will spend its last 10 to the 100th years in complete darkness, after the last black holes evaporate. The stelliferous era, the age of stars, is a brief flare in a story measured in googles. A few trillion years of light bracketed by eternities of dark. We live approximately at the midpoint of the age of stars. The last red dwarfs, the dimmest and most numerous stars, will fade after 100 trillion years, when the universe is 10,000 times older than it is today. They burn hydrogen so slowly that some will survive long after every other kind of star has exhausted its fuel. When the last one fades, the stelliferous era ends. The degenerate era begins. White dwarfs, brown dwarfs, neutron stars and black holes will dominate a cosmos colder and darker and more diffuse. Black holes evaporate via Hawking radiation, a quantum process predicted in 1974. A solar mass black hole takes 10 to the 67th years to evaporate. Supermassive black holes at galactic centers take 10 to the 94th to 10 to the 100th years. If our current understanding of quantum physics holds, even the largest black holes will eventually radiate away into photons and neutrinos, dispersed through eternally expanding space. The Dark Era. After cosmological decade 100. No stellar objects of any kind remain. The universe does not die. It empties, cools, and darkens, expanding forever into a silence that has no witnesses. Darkness is not absence. It is the natural and majority state of the universe. Stars and visible galaxies are the exception. Islands of light in an ocean of structural darkness that came before and will return. The James Webb Space Telescope continues pointing into the cosmic dark. Launched in December 2021, operating from the second Lagrange point 1.5 million kilometers from Earth, it captures deep fields in infrared, measuring redshifts of the earliest galaxies, extending toward the darkness that preceded all stars. What Hubble began with the ultra-deep field in 2004, Webb continues, seeing further back in time, toward the wall of ancient fire that marks the moment the universe became transparent. You are not sleeping under an empty sky, you are sleeping under the oldest light in the universe, under a darkness that has a name, a measurement, a history. Under a cosmos composed mostly of substances that emit nothing. Under a horizon defined by the speed of light and the finite age of everything. The darkness is not absence. It is evidence. Evidence that the universe began. Evidence that it is still young. Evidence that it will continue long after the last star fades. The cartographer has been here. Now rest. The mathematics was sound. The assumption was wrong. In an infinite, eternal, and static universe uniformly populated with stars, every line of sight from Earth must eventually terminate at the surface of a star. The night sky, by this logic, should be as bright as the surface of the sun, not dark, not even dim, blinding. This is the dark sky riddle. And for 3 centuries, it resisted every answer. The farther out you look, the more stars you find, in exactly the proportion needed to compensate for their faintness. Shell by shell, the sky should fill with light. The number of stars at a given distance grows with the square of that distance. The brightness of each star falls with the square of that distance. The two effects cancel exactly. Every shell of space contributes the same amount of light. Summing over infinite shells gives infinite brightness. The darkness of the night sky is therefore direct observational evidence that at least one of the foundational assumptions must be false. Infinite space. Infinite time. Uniform stellar distribution. Something had to give. Thomas Digges raised the problem in 1576. Johannes Kepler posed it again in 1610. Edmund Halley gave it formal treatment in 1720. Jean-Philippe Loy-de-Chazot published calculations in 1744. Heinrich Wilhelm Olbers gave the riddle its name in 1823, but the question had unsettled astronomers for more than 2 centuries before him, and every answer came up short. Chazot and Olbers proposed interstellar dust. It was a reasonable guess. It came apart at the level of thermodynamics. John Herschel refuted it in 1848. In an eternal universe, dust in thermal equilibrium with surrounding stars re-emits exactly the energy it absorbs. The brightness does not disappear, it changes form. Kepler proposed the universe is finite in spatial extent. The stars simply run out at some distance. Mathematically, this resolves the riddle. But a static, finite universe collapses under its own gravity. The solution is physically unstable without expansion. A poet came closer to the answer than the astronomers of his generation. Edgar Allan Poe in Eureka, published in 1848, argued that the dark voids in the sky could only be explained if light from the most distant stars had not yet had time to reach us. He grasped the finite speed of light as the key, decades before physics formalized it. Johann Heinrich von Madler published in 1858 the first solution in scientific literature, combining the finite speed of light with the hypothesis that stars had not always existed. According to Harrison, the first mathematically satisfactory resolution was published by Lord Kelvin in a little-known 1901 paper. Kelvin was unaware of Mädler's work. His resolution was popularized by Harlow Shapley and became the standard solution. But the riddle resisted for 300 years, not from carelessness. Every answer left the universe eternal, and an eternal universe, no matter how dressed, fills the sky with light. The universe has a finite age, 13.787 billion years, measured to within 20 million years by the Planck satellite. This single fact resolves the core of the dark sky riddle. Stars have not had infinite time to fill the sky with light. Light travels at 300,000 kilometers per second. Stars beyond the cosmic horizon simply have not had time to send us their light. The universe is young enough that the sky has not had time to fill. The observable universe is a sphere centered on Earth, with a comoving radius of roughly 46.5 billion light-years. Its boundary is defined by the particle horizon, the maximum distance from which light has had time to reach us since the Big Bang. This is not the edge of the universe. It is the edge of the observable universe. The real universe almost certainly continues beyond, possibly infinitely. The farthest wall we can observe is not a galaxy. It is the cosmic microwave background, emitted at redshift 1100, roughly 380,000 years after the Big Bang, when the universe first became transparent. The oldest light we can observe, a glow released when the universe cooled enough for electrons to bind to nuclei and photons to travel freely for the first time. The universe became transparent, and what it revealed was the void between the stars. The cosmic microwave background photons have been traveling 13.8 billion years to reach us, but the region of space that emitted them now lies at a comoving distance of roughly 45.7 billion light-years. It receded while the light was in transit. Space itself stretches, and light traveling through it stretches with it. This is cosmological redshift. Visible light occupies wavelengths from 380 to 700 nanometers. Ultraviolet and near-infrared light from distant galaxies shifts out of the visible range into the infrared, and eventually radio, invisible to the human eye. The cosmic microwave background itself originally had a temperature of roughly 3000 degrees Kelvin. It arrives today at 2.72548 degrees above absolute zero, in the microwave range at wavelengths near 1 millimeter. The oldest light in the universe arrives today as invisible warmth, a whisper at 2.7 degrees above absolute zero. Finite age explains the darkness. Expansion deepens it. Both effects act in the same direction. Finite age dominates. The universe is not dark because it lacks light. It is dark because most of its light has been stretched beyond what our eyes were built to see. Between September 2003 and January 2004, the Hubble Space Telescope pointed at a rectangular patch of sky in the constellation Fornax. 2.4 arc-minutes per side, roughly 1/10 the angular diameter of the full moon, a patch of sky smaller than a grain of sand held at arm's length. 800 exposures across 400 Hubble orbits. Total exposure time 11.3 days. Where the sky appeared empty, Hubble found it full. Not of stars, but of entire universes. The Hubble Ultra-Deep Field contains an estimated 10,000 galaxies, including some of the most distant known at the time of publication, existing 400 to 800 million years after the Big Bang. Nearly every point of light in the image is a complete galaxy. The few visible stars, barely 7 within the Milky Way, are identifiable by their diffraction spikes. Everything else is an island universe. each containing billions of stars at distances of billions of light-years. Somewhere between hundreds of billions and 2 trillion galaxies populate the observable universe. A number so large the difference barely matters to the imagination, but that astronomers are still arguing about. And yet the night sky remains dark. The universe is composed, according to the Planck satellite's final measurements, of 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. 95.1% of the universe does not emit, absorb, or reflect electromagnetic radiation in any currently detectable form. Dark matter does not interact with light at all. It passes through electromagnetic radiation as if it were not there. Its existence is inferred exclusively from gravitational effects. Fritz Zwicky first proposed its existence in 1933, studying the Coma cluster. Vera Rubin and Kent Ford confirmed it independently in the 1970s via spiral galaxy rotation curves. The stars are moving too fast. Something unseen is holding them in place. Dark energy is not matter. It is a property of space itself, or possibly a form of vacuum energy, associated with Einstein's cosmological constant. It was discovered in 1998 independently by 2 teams observing distant Type Ia supernovae. The expansion of the universe is accelerating, not decelerating. The more space there is, the more dark energy there is, and the faster the expansion accelerates. 2 darknesses. One that holds galaxies together. One that tears the universe apart. Both invisible. Both dominant. Neither understood. Ordinary matter, everything that forms stars, planets, gas, dust, and human beings, constitutes only 4.9% of the energy content of the universe. We built our entire understanding of the cosmos from 5% of what exists. The other 95% has been there all along, shaping everything, untouched by light. The universe is currently in the stelliferous era, the period in which energy is generated by the birth, life, and death of stars. We live approximately at the midpoint of this era. The stelliferous era spans from roughly 1 million to 100 trillion years after the Big Bang. The universe is currently roughly 14 billion years old. The last stars to die will be the dimmest ones. Red dwarfs, barely glowing, hoarding their hydrogen for trillions of years. When the last one switches off, the universe will be roughly 100 trillion years old, 10,000 times its current age. After the stelliferous era comes the degenerate era, dominated by white dwarfs, brown dwarfs, neutron stars, and black holes. No light from ordinary stars will illuminate any sky. Black holes eventually evaporate via Hawking radiation, a quantum process predicted by Stephen Hawking in 1974. A solar mass black hole takes roughly 10 to the 67th years. Supermassive black holes at galactic centers take 10 to the 94th to 10 to the 100th years, if our current understanding of quantum physics holds. The final state is the dark era. After 10 to the 100th years, when even the last black holes have evaporated, no stellar objects of any kind remain. The universe will consist of photons, neutrinos, electrons, positrons, and sparse radiation dispersed through eternally expanding space, approaching absolute zero. The universe does not die. It empties, cools, and darkens, expanding forever into a silence that has no witnesses. The night sky is dark not because the universe is empty, but because it is young. 13.787 billion years. Finite, not eternal. Because it is expanding, and light redshifts into infrared and microwaves beyond the visible range. Because it is composed mostly of substances that emit no light. Darkness is not absence. It is the signature of a universe with a history, with boundaries, with a physical constitution. Darkness is not the anomalous state of the universe. It is its natural and majority state. Stars and visible galaxies are the exception, islands of light in an ocean of structural darkness. The cosmos spent its first 380,000 years in complete darkness. It will spend its last 10 to the 100th years in complete darkness. The age of stars is a brief flare in a darkness that came before and will return, a few trillion years of light in a story measured in googles. The darkness of tonight's sky contains the particle horizon at 46.5 billion light-years, beyond which light has not had time to arrive. It contains the cosmic microwave background at 2.72548 degrees above absolute zero, the last light from the moment the universe became transparent. It contains dark matter and dark energy constituting 95.1% of the universe, emitting no detectable photon. Darkness is not simple. It is layered, physical, measurable. The James Webb Space Telescope continues pointing into the cosmic dark, capturing deep fields, measuring redshifts of the earliest galaxies, extending toward the darkness that preceded all stars. What Hubble began in 2004, Webb continues in infrared, seeing further back in time. You are not sleeping under an empty sky. You are sleeping under the oldest light in the universe, under a darkness that has a name, a measurement, a history. The darkness is not a threat. It is the shape of the universe at rest. And you are inside it, on a warm planet, under a sky that is dark, precisely because the universe has had enough time to become something. We've traveled from a riddle posed in 1576 to the edge of the observable universe and beyond, into a future measured in googles. The darkness you see when you close your eyes is the same darkness that fills most of the cosmos. Not emptiness, but the natural state of a universe composed mostly of things that emit no light. Tonight, when you look up, you're not looking at absence. You're looking at a physical signature, the finite age of the universe, the stretching of space, the dominance of substances that emit nothing. The sky is dark because the cosmos has a history. Some of you fell asleep hours ago. Some of you stayed. Both are exactly right. Wherever you are, under city glow or open sky, in winter or summer, alone or beside someone breathing, the dark will still be here. So will I. Tomorrow night, if you'd like to return, the door stays open. Another map, another corner of the cosmos, another long walk into the structure of things. Rest now.